Chapter 2 can be generally described as three separate segments. The first segment talks about the words that we use to describe motion, like speed, displacement, velocity, acceleration, and they would have their own formulas. The second part would, of course, be the part where we look at the graphs. So that's going to be the graphical interpretation part. And finally, you need to consider this last part, which is about free fall. So let's jump first into the first section concerning something similar to what we did before of scalars and vectors. We all know very well what speed is, correct? Speed would just be distance divided by time, and when it comes to SI unit, we will be using meters per second. Now, the next part we want to consider will be average speed, and that will be total distance over total time. This is especially important when we go to the graphs and you can read off the graph what is the actual total distance that's covered. It's easy to find the average speed once you look at total distance over total time. Now, let's go on to the vector versions. If I'm looking at speed, what would then be if I'm looking at velocity? Much like speed, we are looking at meters per second or km per hour. But what's different is that now, because it's a vector, we cannot use distance, we use displacement. Now, if you recall, the difference between distance and displacement is that one's a scalar, one's a vector. If it were to be drawn like as a diagram, this is what it looks like. If the blue is my actual distance, which is the path I actually covered to go from point to point B, well, what would then be displacement? Displacement would be in one direction from start to end in a straight line. This would be my displacement. Displacement would not be the same as my distance. Displacement would just be the distance between 2 points in a straight line. Take note for all of this when we talk about speed or velocity is how my distance or displacement is changing over time. Now, when we look at the next part, which is acceleration, we no longer look at how the distance changes over time. We're looking at how the velocity changes over time. I didn't say speed because acceleration is a vector. It has direction. It depends on what you consider to be a positive direction. Looking at this car, you would see that this car is moving at a speed of 5 meters per second, but I can't tell you the velocity unless I know what is the positive direction. Now, if I were to say that to the right, moving towards the right is a positive direction, then sure, it's moving at 5 meters per second. But if I were to say that left, take left to be positive, then this is no longer moving in a positive direction. This is going to be moving at negative 5 meters per second. In this case, because left is positive, negative 5 meters per second would tell you that it's moving at this quantity, this magnitude, but in the opposite direction from what I considered to be positive. So that's the difference. So now let's talk about our acceleration. Sorry, it took a while to get there. Now, the definition of acceleration is important. It is the rate of change of velocity, which means how fast does it change? Wow, that doesn't sound very easy, right? When you use the word fast. So let's go this way. In every 1 second, how much does my velocity change? So this information is important because if you were to look at the car on top, and then I were to look at another point in time when I see the same car, and that car now is moving at 6 meters per second. Now, the acceleration depends on how long it took to go from 5 meters per second to 6 meters per second. If I were to say that in 1 second, right, compared from here to there, in 1 second, it changed from 5 meters per second to 6 meters per second. Ooh, I can see that, oh, that acceleration is, wow, how much is that acceleration? Big, small, a lot, little bit. It's better to actually use numbers. So let's try to use a formula. If it's how it's changing, how the velocity is changing for every 1 second, the formula then be acceleration is to v minus u over t, where my v represents my final velocity or at the very end, and my u represents my initial TIAL. Oh dear, what's wrong? Initial velocity, right? So if we looked at our question over here, at first it was 5, the last velocity was 6. So it would be 6 meters per second minus 5 meters per second, and it took 1 second, isn't it? So I will say that this would be 1 meter per second squared. Now, let's assume that there was also another set of cars, first moving at 5 meters per second, then moved at 6 meters per second, but it took the car a total of, let's say, 5 seconds. In 5 seconds, it took 5 seconds for it to change from 5 meters per second to 6 meters per second. Now, in your head, you will probably be able to really say that, oh, that acceleration is much less compared to the first example we gave, isn't it? Yes. And if you were to use our formulas, v minus u over t, we can use the same thing, right? Final will be 6, initial will be 5, but it took a grand total of 5 seconds, right? I'll get 1 over 5. Whoop, wait a minute. We do not use fractions. We cannot end off as a fraction in physics, so 1 divided by 5 would be 0.2 meters per second square. And now comparing these two numbers, I would say in the first case where I change speed 5 to 6 in 1 second, this acceleration is greater, this acceleration is smaller. Another way of looking at acceleration is that, well, in every 1 second, my velocity changes by a positive of 1 meters per second. In this case over here, in every 1 second, my velocity changes by a positive 0.2 meters per second. All right, now there are other ways to use this formula. Sometimes they tell you the acceleration. You need to figure out what are the initial or the final or the time taken for the whole movement to occur, right? Let me show you an example. For example, let's say I have a car and I'm going to tell you that it's moving at a constant acceleration, and the constant acceleration is 20 meters per second square. I'm going to tell you that when I first look at it while it's moving, right, at that point in time, it is moving at a speed of, let's say, 10 meters per second. So the question I have, right, would be after 2 seconds, right? After 2 seconds, what would the speed be? What would the final speed be? So how do you do that? Well, first I'm going to mark out, oh, this over here, that's acceleration, A. This over here that was given to me in the explanation, I said that was the first speed. So I'll say that's my initial speed, this is my U. And the question asked me after 2 seconds, what will be the final speed? So this over here would be T, and the question is asking me to find V. So what it would look like is that I must always put in my formula first. I've recognized that this requires me to use my acceleration formula. There's no graphs yet. Now I just substitute 20. I do not know what's V, but I know U is 10, and I know this over here is 2. So my working would look similar to this. Take note of my units. Because I wrote I'm calculating velocity, I remember my units is meters per second. I don't write meters per second squared because that only belongs to acceleration. Alright, so these are some of the questions which require you to use the formulas and remember all the different descriptions of speed, velocity, acceleration, displacement. Now let's move on to the graphs, because this is where most of the marks actually come from for this chapter. Graphs. Graphical approach, we're looking at my displacement time graph and my velocity time graph. When you say displacement time graph or velocity time graph, it just tells you what's on the y and x-axis: displacement time, velocity time. Now, because we are dealing with graphs, something that we know from mathematics is that when it comes to graphs, a big thing that we will want to consider would be the gradient. Now, gradient would always be looking at the change of y over x, correct? Change in y over change in x, of how my y value changes my x value. Which brings into a very interesting question. If I were to look at displacement time graph here, displacement time. Now, displacement is y, time is x, correct? Now, a change of y over x would give me my gradient. But in this case, if I look at my formula, it tells me that if I look at the gradient of the displacement time graph, it actually tells me velocity, isn't it? Now, likewise for acceleration, acceleration is going to be a change of velocity over time, correct? Velocity over time, which tells me that the gradient of a velocity time graph would give me acceleration. Now, just a bit more about gradient. If we were to look at a typical graph, so let's zoom in over here for a while. I would say that comparing this black to this blue, right, the gradient of blue will be less compared to the gradient of the black, right? Because it's steeper, this will be smoother compared to steep, right? So just the lingo that I use, I'm comparing between steep and smooth. Now, this is when the gradients are constant, doesn't really change, okay? Excuse my drawing. These are two straight lines, doesn't really change, it's constant. But once you have a graph where it's curved like this, then I need to start describing how that gradient changes as I go along, correct? Now, as you can see, when it's more vertical, that's steep. When it's more horizontal, that's smooth. This is going from a more horizontal to a more vertical. I would say that's going from smooth to steep, right? So if I'm going from smooth to steep, I would say that my gradient is increasing. But if I had a graph that looks something like this, sorry, I just ran out of color. Let me change color. Ah, like that. Okay. So how do I describe that? This is more vertical, correct? This is more horizontal. This means it's steeper to smooth. So what happens if I go from steep to smooth? What's happening to my gradient? My gradient would be one which is decreasing. So if I go from steep to smooth, that's a decreasing gradient. Now, why is this important? It's because we'll be using these concepts of changing gradients to describe what's happening in our graph. So let's look at the displacement time graph. You are required to be able to, let's zoom in over here. For displacement time graph, you need to figure out when the body is at rest, moving with uniform or constant velocity, and moving with non-uniform or um, changing velocity. So let's see how we can work that out. Remember and recall that we are talking about gradients, correct? So when a body is at rest, it means what would my velocity be? Let's try to interpret this in terms of velocity, okay? If I'm at rest, it means my velocity would be 0. Does it mean it's constant velocity? Well, no. It's going to be more important to say that this is 0 velocity rather than constant. Isn't it constantly 0? Yes. That is more important information to tell me that it's 0 velocity. Okay. Now the second one says moving with uniform velocity. I would say that this is constant velocity. That means there is a velocity, velocity. What's wrong with me? There is a velocity, and its constant is not changing. Now, what about moving with non-uniform velocity? I would say that this over here is changing velocity. Now, interesting. If we were now to go and look at what we said before, right, that the gradient, when I'm looking at displacement time graph, gradient tells me velocity. I could actually just change all this to, hey, this over here is 0 gradient, correct? I will have a graph that looks like a 0 gradient graph. If it's constant velocity, it will tell me that it's going to have a constant gradient, right? That means it's a straight line. And then when I see one which has a change in velocity, it tells me that I'm going to have a graph where I have a changing gradient. And of course, the way I'm going to describe the changing gradient would be whether it's increasing or decreasing, depending if it's steep to smooth or smooth to steep. Now, I know that here. How does it look like here? So let's draw a few graphs and let's see whether we can use the gradient idea to describe which is at rest, which is constant, which is increasing, or maybe, you know what, let's go with increasing speed and what's a decreasing speed. Okay, let's draw 4 graphs. All right, let's use the understanding of gradient to tell us what is the velocity like, whether it's at rest, no velocity, whether it's constant speed, whether it's accelerating, decelerating. Okay, so let's try it with the red one first. The red one over here, we're going to use the idea of gradient. What is a gradient? Oh, it's a straight line, constant gradient. But wait, is it just constant, or is the better understanding of this gradient description to be 0 gradient? There's no change, right? So this is a 0 gradient graph. 0 gradient, 0 gradient, no 0 gradient, 0 velocity. This is at rest. Let's try again. Once again, for this graph, for this displacement time graph, let's look at blue. This is a straight line. Oh, that means I have a constant gradient. Constant gradient, constant velocity. It tells me that the blue graph has constant velocity. Now, I can even go one step further, especially when it comes to constant velocity. I could look at 2 points. I could maybe look at this point over here and this point over here. Let's just say that this is 10. And at this point over here, let's say this is 5. So what is the velocity at that point in time? Hmm? Well, velocity is gradient, isn't it? And because it's constant gradient, I can calculate it. What is the formula? Gradient is change of y over change of x, right? So the change is, well, if you look at it this way, this has 5. Oh, wait a minute. Is this the correct way of doing it? No, 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 no. We have to remember it's x and y, right? To coordinate pair, x value is 5, y value is 10, correct? Now, at this point over here, x is 0, y is also 0. So I can find gradient is y2 minus y1 over x1 minus x1. So y2, so let's take this as y2. This is y1, x2, x1. 5 minus 0, sorry, 10 minus 0, 5 minus 0. Gradient is 2. So in this case, if gradient is 2, my velocity, my constant velocity in this case would be 2 meters per second. All right, so I've done the red, I've done the blue. Let's try the green over here. Now, clearly, this gradient is changing. It is non-uniform. Uniform, non-uniform. But how's it changing? Is it getting from smooth to steep or steep to smooth? Let's check. Steep, smooth, smooth, steep. It looks like it's going from horizontal to more vertical, correct? It's going from smooth to steep. Oops. Smooth to steep. Smooth to steep means it's increasing gradient. Therefore, I can simply say that increasing gradient, increasing velocity, speeding up, right? It makes sense, correct? Because to make a change of displacement from this time to this time, I only change this much displacement, correct? That's how much my displacement changed. But between this time and this time, my displacement changed by so much more, correct? Or rather, I'll look from here. Okay, what's next? This is increasing velocity. What about this one over here? I'm gonna write down the side. Increasing velocity. Increasing velocity. What about the yellow line? This is quite steep, then it gets quite smooth, isn't it? So this over here, looking at gradient, my gradient is decreasing. Decreasing gradient, decreasing velocity. And interesting, look at this over here. You realize this is similar to this? It goes until there's zero gradient. That means this is decreasing velocity, decreasing gradient, and then after that, I'm not moving anymore. This is zero velocity, right? Because from this time to this time, my displacement didn't change, I didn't move, so I'm not moving anymore. So the yellow color one would be decreasing velocity until it gets to zero velocity, until it comes at rest. What about this purple one? Well, in terms of displacement, am I going further away from my start point or am I getting from far away towards the start point? Well, I'm going back, isn't it? See, at this time over here, I'm this far away. But closer to the end time, oh, I'm not too far away from where I'm measuring from, isn't it? So it's actually coming towards me, right? From here, far from me, here, close to me. Everything else is going away from me except for this guy, right? The red color one at rest is 10 meters away from me at the start. At the end, it's still 10 meters away from me. All of these things are getting further from me. Purple line shows it's coming towards me, right? So let's look at the gradient. Is it getting steeper or getting smoother? Steep to smooth. Oh, steep to smooth. That means it is a decreasing gradient. Decreasing gradient, decreasing velocity. So, decreasing velocity. So this guy is slowing down. Slowing down, same speed, at rest, no speed, speeding up. So this guy is slowing down. It's kind of like reversing towards you, and then after that he slows down. At first very fast, then slowing down. This is looking at the gradient for displacement time graph. What about if we did something similar for the velocity time graph, but this time remember that if I look at gradient, this tells me acceleration. Now, one thing that we want to consider over here is that it gets just a little bit more detailed when it comes to this part. See, if once again we draw this, correct, you would say this over here is a positive gradient, correct? This is positive. But once you do this one over here, this way, this would be a negative gradient. Now, we did say when it comes to vectors, right, positive or negative just tells you direction. And that's especially important when you're talking about deceleration or acceleration. So let's give this a try. Now, let's not talk about any change in gradients for now. Let's just look at everything where it's all straight lines. So gradient in a velocity time graph talks about change in velocity over change in time. That means acceleration. So every time I think of a gradient in a velocity time graph, I'm talking about acceleration. So let's try this one over here. Let's look at this one over here. Is there any gradient? Any gradient? No gradient. No gradient, no acceleration. But there's a bit more details to it, you see? Now, it tells me for this velocity time graph, right, my velocity is 0. It was 0 at the beginning, is 0 at the end. This over here, I would say it's at rest. Oops, wrong color. I can also say 0 acceleration because I understood the gradient, but once you're talking about at rest, I think that's the most important detail to know. Now, how do I compare this red line to the blue line? You see, the blue line over here, right? There's a coordinate over here, right? Let's say if this over here was 5. Okay, let's say for example, it means that when time is equals to 0, when time was 0, my speed or velocity was 5. And it continued to be 5 meters per second throughout the entire time. So that means I'm moving at constant speed. Wait a minute. How do I use gradient here? Remember that if it's a velocity time graph, first talk about the gradient that links to acceleration. So that means, hey, velocity time graph, lost my gradient. Zero gradient. Zero gradient means no acceleration. Zero acceleration. So that's great, but let's go further into details. Zero acceleration. Is it at rest or is it at constant speed? In this case, blue line, this is at constant speed. So I'll say this is constant speed, and I'll tell you the speed is 5 meters per second. All good? Let's try the green color line over here. Okay. Now, this over here has a gradient. Now, this gradient is one which is a positive gradient. Recall? Positive gradient. And you would also see something very, very easy. Just look at your coordinates, okay? Based on coordinate, if I were to look at this first coordinate over here, compared to the coordinate over there, this coordinate tells me that when time is equal to 0, I have no velocity. But at this point over here, right, my velocity clearly increased, correct? Because I actually have a y value over here. I sped up. I'm increasing in velocity. That means I have accelerated. Now that makes a lot of sense because now we say that gradient is acceleration, correct? Is there acceleration? Yes. And it is constant acceleration. And it's a positive constant acceleration. I would say that this over here is accelerating. And it is constant acceleration. Much like what we did before, I can actually calculate this gradient, right? Looking at these two coordinates over here, I can find my acceleration, and that looks strangely like what we did over here, isn't it? Final versus initial over time. If let's say this over here, this one, okay, let's find a coordinate pair. Let's assume that this time over here is maybe, let's say 10. Okay, so and let's also assume that this over here hit maybe 11. So my coordinate pair over here, this would be 10, 11. And this over here would of course be 0, 0, right? What is my acceleration? What's my constant acceleration? I'll say acceleration would be y2 minus y1, x2 minus 1, 11 minus 0 over 10, which is very interesting, correct? Because this is my final velocity, this is my initial velocity, and 10, that's the time taken, isn't it? So over here, I'll get an answer 1.1 meters per second square. I could do the same thing for the yellow color line, but what's important to note is that if I were to look at the coordinate over here, at 0 seconds, I had a certain velocity. Let's say maybe this is 10 meters per second. And over time, what happened to my velocity? You can tell, right, that at this point, my coordinate, this is much less. Let's say if this touched all the way down to the bottom over here, correct? At this point, this is 0. I had a velocity and then it became 0. Clearly, I'm slowing down. Now, this makes a lot more sense also when I consider the fact that I know that this is negative, correct? What is negative acceleration, right? Negative acceleration, that means my acceleration is going the opposite direction. In this case, I can say that this is decelerating, right? Of course, if I were to continue going backwards, which is another graph I will have to draw, there will be negative acceleration. I could be actually speeding up in the opposite direction. Okay, but for now, this is decelerating, and I can calculate also this gradient. Let's go to ones where my graphs are changing gradients. Let's do it over here. So let's try to describe the gradients first, okay? So let's try red graph. Let's go first. Is it positive or negative gradient? Positive is going upward, right? So positive. So I know that it's a positive gradient. It's going to be acceleration. So that's acceleration. But how is the gradient changing? Smooth to steep. Oh, increasing. Increasing. Okay, so I know it's acceleration. It's not deceleration, and it's increasing. So this over here would be increasing acceleration. Let's do the blue one. Okay, so is it speeding up or slowing down? Speeding up, right? It's a positive. Is a positive, negative gradient? Positive. Oh, acceleration. Nice. That's an easy way of looking at it, right? So acceleration. How is it changing? Is it getting smooth to steep or steep to smooth? So it's this one's more vertical. This is more horizontal. It's going steep to smooth. It is decreasing. Decreasing acceleration. There you go. Decreasing acceleration. Right? So it's almost like I'm asking the back word first, then the first word, right? The front word. The back word reminds me it's acceleration. I'm speeding up. It's positive gradient, it's acceleration. Then after that, is it increasing or decreasing? Let's try again for the green one. Okay, let's find the back word. Is it acceleration, deceleration? Am I speeding up or slowing down? I went from a high velocity to a zero velocity, correct? Clearly, I'm slowing down. Deceleration. Let's check again. Is this positive or negative gradient? Well, this would be one of a negative gradient, correct? Okay, deceleration it is. Deceleration for green graph, how is my gradient changing? I know it's deceleration, not acceleration, but is gradient going steep to smooth or smooth to steep? Smooth, right? Horizontal to vertical, smooth to steep. It's increasing deceleration. So I know that it was deceleration. Was it increase? Oops. I just realized that this looks like deceleration, acceleration. This was decreasing, increase, decrease. So I wrote out deceleration. And because it's smooth to steep, this is increasing deceleration. Okay, increasing deceleration. And the yellow one, again, I know it's slowing down. I know it's negative gradient, so it has to be deceleration. So I'm going to write the first one. Okay, it's deceleration. But how is it changing? How's the gradient like? Is it steeper to smooth? Steep to smooth. It is decreasing. My gradient decreasing, decreasing deceleration. All right. Is there anything else that we need to know for my velocity time graph? Yes, it would be this, that if I were to look below the graph, what on earth does below the graph mean? Let me show you. If I were to look at my red color graph, let's say I want to have a certain time. Okay, here. At this time, how far did each of these graphs, blue, green, red, and yellow, how far did they go? So the question is, what is the distance traveled, or displacement. So what is the area below the graph at t? So for the yellow, the area below graph would be here. What about red? The area below graph of red would be here. What about green? What's the area below graph for green? Well, it would be here, right? What's the area of graph below blue? Well, it will be here. Just by shading, you can tell, right, that the one of the biggest area would mean that's the one which has the greatest displacement. In this case, right, the green graph is the one which moved the most, right? We're just looking at the area below graph. So it's not just using distance, speed and time. No, right? When we use the displacement, we use the velocity time graph, look at area below the graph, right? So likewise, if I were to look at this, let's say if I'm looking at this time over here, t, can you tell which one has moved the most in time from time 0 to time t? Well, I could do it by looking at what's the area in the graph, right? Red cannot draw lah, right? There's no area below the graph. Take note that I drew this black line freehand. So there's no area. Well, it didn't move. It's at rest, clearly. See for the green. Green would be, this is the area. Technically, I can use a triangle, right? I can find the area. What about blue? Blue would be, oops. Blue would be this. And yellow would be this, right? So the movement depicted by the yellow graph, that one moved the most in time 0 to time t, right? Okay, final part. We need to talk about state that the acceleration of free fall for body near the Earth is constant and approximately 10 meters per second square. Okay, so what would this be? So this one is going to be a bit careful because I want to make sure what is the positive direction. So let's say, for example, right, if a person that's diving into the water, let's say it's going to dive straight down this way. Correct? So how does acceleration of free fall look like? So here's the thing that we want to say that if I'm not considering, which is actually the next chapter, if I'm not considering any air resistance, okay, now everything on Earth will accelerate at a value of 10 meters per second square, which means every 1 second my speed increases by 10 meters per second. So how does that look like? This would be one where it is a constant acceleration where I'm speeding up. Now, I like to say that I want to have downwards to be positive. Okay, so I start at 0 meters per second and I'm going to hit the waters at quite a fast speed. So, how does it look like? I will now draw one which is constant acceleration. Acceleration for velocity time graph is gradient, correct? It's going to be a constant gradient. Now, I did say that I'm speeding up, correct? That means I'm going to accelerate. That means it's going to be a positive graph. So what it will look like is something that looks like this. Now, does it make sense to you? Let's try. I start from 0. As I go along, I speed up, and it's a constant acceleration because acceleration due to free fall is 10 meters per second square, which would mean that every 1 second, if this is 0 and this is 1, every 1 second my speed increases by 10 meters per second. If this over here is 2, this over here would be 20. Wow, that's crooked. Sorry, 20 meters per second. This is acceleration due to free fall. It doesn't matter if it is 1 kg of feather or 1 kg of like bricks. Everything falls at the same rate. Everything falls with an acceleration of 10 meters per second square. Every 1 second, it increases at speed. This is when we are not considering any air resistance. What is wrong in my handwriting? Resistance. Okay, we're just saying that acceleration to free fall is going to be 10 meters per second square, and it will look something like this. In the next chapter, you'll get something that looks like this over here, where my gradient actually changes. My gradient gets smaller. My acceleration actually gets smaller. I have a decreasing acceleration, but that's when I'm actually starting to consider air resistance. But in this case, this part, We are saying that acceleration due to free fall, that's not sorry, acceleration of free fall, my bad, would be where I accelerate based on what is the gravity on Earth. And the gravity that we have on Earth gives us an acceleration of 10 meters per second squared. Ooh, maybe we can do one more question. Let's compare um, between Earth and the moon. All right, clearly you know that on the moon, my gradient, sorry, not my gradient, um, gravitational field strength on the moon is way less than what we have on Earth, right? So here's a question, okay? If I were to look at a velocity time graph of something dropping on Earth as compared to the moon, which would it look like? Would it look like this, whereby on Earth, on moon, sorry, Earth and moon, or would it be, these are both velocity time graph, okay? Would it be A or B? Where this is Earth and this is moon, okay? Where these two are supposed to be parallel. Which one would be the correct answer? A or B? Which one would explain how it has different acceleration of free fall based on the gravity that you're going to experience on different places? The answer cannot be B. You see, in these two cases, if these were parallel, it would be to say that it has the same gradient, the same acceleration, and that's not true, right? If I have a greater, if my gravity is greater on Earth, that means the acceleration is going to be greater, correct? So this would be correct because the gradient is greater, this has a lower gradient. Answer is this one. This one we depicted properly, this does not make sense. Okay, that's most of the things that you should know. Don't think really can cover this. It's already 38 minutes already. But this is are the main ideas you should know when it comes to kinematics. Talking about the descriptors of speed, velocity, acceleration, talking about the graphs, and then talking also about what is acceleration of free fall. And that should be 10 meters per second square. Whew, okay, there you go, guys. Bye.